We have a couple of equations for power. Please give me one equation for power. Mr. B. Force times velocity, we're not going to start there because we'll end there actually. But force times velocity, true. Power. Fine, we'll go with the other people. The change in work over the change in time. You can also have power equals the derivative of work with respect to time. What is the difference, Catherine, between these two types of power?
One is when the work is...
Sorry, say again?
Wait, one is work without one is work that's different over time.
No, that's okay. You're missing the difference. That's okay. Travis?
The first one's average power, and the second one is at a certain time.
Instantaneous power. So this first one is the average power, and this one is instantaneous. In other words, the power at a specific point in time. What are the dimensions on power? Michael? Newton meters per second. What is a Newton meter called, Meg?
A joule.
A joule. What is a joule per second called, Jenkins?
Is it watt?
Watts. So it is joules per second, which is in watts. We also have the convenient conversion from 746 watts is what, class?
Horsepower.
1 horse, your standard horse, 1 horsepower. That is not on your equation sheet as far as I can tell. However, it is something that if you do need it, will be given. It's not something that you need to memorize. You don't need to memorize that. Remember, power is how much work is done in how much time. It's the rate at which work is done. Let's do so. I'll show you that now. Rate at which work is done. All right, let's do an example. Let's say, let's finish this. So if power equals the derivative of work as a function of time, work with a constant force. What is the equation for work with a constant force? Here. Gary?
Force times delta R.
We have F delta R times the cosine of theta. So what we have, bless you, if the force is constant, let's actually do this. The derivative with respect to time of F delta R times the cosine of theta. If the force is constant, then it's going to be the derivative of the position. So it's going to be equal to force times the derivative of position with respect to time times the cosine of theta. What is the derivative of position with respect to time? Victoria. Derivative of position with respect to time. Velocity, which brings us to the equation Rohan gave us at the very beginning. FV cosine theta, or the scalar product slash dot product of force and velocity, is also power. Where theta, of course, is the angle between the force and the velocity. So let's do an example. Let's say we have a mass which is equal to 0.280 kilograms, and we know the position as a function of time of that mass is equal to 5.00 t cubed minus 8.00 t squared minus 30.0 t meters. The question is, what is the net power at 2.00 seconds? The net power at 2.00 seconds. First, Mohit, are we asking for an average or instantaneous power?
Instantaneous.
Instantaneous, but you know this because?
Because you give us function.
Not quite. We could actually figure out the average power even if we had a function.
You were asking that at a specific time.
At a specific point in time, which is instantaneous rather than average. If I asked for the net power between 0 and 2 seconds, that would be an average, whereas this is at 2 seconds, so that's an instantaneous. Thoughts on how to solve this problem? Emily?
Should we find the velocity function?
Okay, sure, we can find the velocity function. How are we going to find the velocity as a function of time? Dorset? Of the position as a function of time. Please take the derivative of the position as a function of time, Hillary.
15t squared minus 16t minus 30.
Okay. This is the velocity. So we have the velocity as a function of time. Our goal is to figure out the net power at 2 seconds. We have the velocity. What else can we do? Gary?
How sure this should I put do the acceleration?
I don't know, let's find acceleration. How would we figure out the acceleration as a function of time? Eugene?
The derivative velocity as a function of time.
Good. Derivative of velocity as a function of time. Stazel, please take the derivative.
30t minus 16.
That's in meters per second squared. So what type of motion is this not? What? No, actually, we know that, but that's not quite what I'm going at. We could, I guess, list all sorts of things it is not, but I'm looking for something specific. Bailey? It's not uniformly accelerated motion, right? You can see the acceleration is going to change as a function of both position and time. Great! We've figured out the velocity and the acceleration. We're trying to figure out net power. I still don't know where we're going. Jenkins?
You can find force by using Newton's second law.
Ah, Newton's second law. Mr. Lee, what's Newton's second law?
The sum of the forces equals mass times acceleration with vectors on force and acceleration.
We are looking for the net power, which means we're using which force, class? Net force. Net force equals mass times acceleration. So we have the net force now. It's equal to the mass multiplied by the acceleration, which is 30t minus 16. So we have the net force. We can plug in numbers in a little bit. We're not quite there yet. We're looking for the net power. What equation we're going to use to figure out the net power? Bill?
Can you say that again?
What equation are we going to use to figure out the net power at 2 seconds?
The net power. FV cosine theta.
We're going to use F dot V or FV cosine theta. So this is the net force and the net force. So we have the net force, which is mass times 30t minus 16. And we even have the velocity. The velocity was given as 15t squared minus 16t minus 30 times the cosine of theta. Let's plug in some numbers here. The mass was 0.28 multiplied by 30 times the time, which was 2 seconds, minus 16. Multiplied by 15 times 2 squared minus 16 times 2 minus 30 times the cosine of theta. What do we get? Please.
-24.64.
We still have the cosine theta hanging out there, so we kind of have to figure that one out. Theta. It's going to be the angle between what and what? How's it?
Force and velocity.
Force and velocity. We need to figure out the direction of the force and the velocity. The net force is going to be the direction of what? The acceleration. So we need to figure out the direction of the acceleration and the velocity, and we need to figure it out at 2 seconds. Everything's in the x direction, so the velocity at 2 seconds is equal to 15 times 2 squared minus 16 times 2 minus 30. What do we get? Negative 2. The acceleration at 2 seconds is, we have 30 times 2 minus 16. 44. So what do we know about theta then? Zach?
It's opposite of, or it's 180 degrees.
180 degrees. The velocity is in the negative x direction, the acceleration and the net force is in the positive x direction. Therefore, we have the cosine of 180 degrees. So negative 24 times, or 0.64 times the cosine of 180 degrees. So the net power is equal to 24.6 watt, Tim? Watts. Great.